Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. Today we will discuss canonical transformations, which are important transformations which leave the form of the equations of motion invariant, particularly Hamilton's equation of motion invariant, from the paper Classical Mechanics. After studying this module, you should be able to understand and learn that in canonical transformations, the Hamilton's equations of motion retain their form. You will learn to generate canonical transformation from a generating function, and given a set of transformation, you will be able to learn to check whether these transformations are canonical or not. The Hamiltonian formalism provides us with a deeper insight into the formal structure of mechanics. We saw earlier that in terms of solutions of a dynamical problem, the formalism does not provide any simplification as compared to the corresponding Lagrangian formalism. However, since it treats the coordinates and momenta on the same footing, it plays an important role in the formulation of quantum mechanics. In macroscopic systems with large number of degrees of freedom, like a thermodynamic system, the formulation of statistical mechanics for the study of such system leans heavily on the Hamiltonian formalism. So, in this context, an appropriate choice of the generalized coordinates and their conjugate momenta is important, and hence the importance of the transformations. What are canonical transformations? A dynamical system with n degrees of freedom can be completely described in terms of its Lagrangian, which is written in terms of a suitable generalized coordinates and generalized velocities. The choice of a particular set of generalized coordinates is arbitrary, but in practice, it is chosen as to simplify the equations of motion. For example, for a central force motion of a particle, the choice of spherical polar coordinates is more appropriate as compared to the Cartesian coordinates. The Lagrangian, written in terms of the polar coordinates r, theta and phi, for example, would not contain phi explicitly, which then is a cyclic coordinate, and the corresponding conjugate momenta then, which is given by the partial derivative of L with respect to phi is then a constant of motion. In the Hamiltonian formalism, the Hamiltonian is defined as a function of two independent variables, is defined as h is equal to sigma pi qi dot minus the Lagrangian, and this is considered as a function of two independent variables. Which are the two independent variables? N generalized coordinates q1, q2, qn, and n corresponding conjugate momenta p1, p2, pn. If a coordinate qi is cyclic, it does not appear in the expression of the Hamiltonian, and the Hamiltonian equation for this qi dot, namely qi dot is equal to partial derivative of h with respect to pi, is constant because the pi corresponding to the cyclic coordinate is constant. The solution qi of this equation can be easily obtained by integration, and we get qi is equal to omega t plus beta, where beta is some constant and omega is a function of constant pi, so omega is also a constant. It is therefore important to consider transformations from one set of coordinates qi to a new set of coordinates written as capital Qi. The new coordinates can be expressed in terms of some function of the old coordinates qi and the time t. That is, capital Qi is a function of the old coordinates qi's and the time t, where q stands for the set q1, q2, qn. These transformations are known as point transformations. Now remember that Hamiltonian formalism, we have a set of 2n variables consisting of n coordinates and n conjugate momenta, and they are treated as independent variables. The concept of transformation from the old coordinates to the new coordinates is widened to include a simultaneous transformation of coordinates and momenta. So we have a transformation from the old coordinates q and conjugate momenta p to the new coordinate capital Qi. So capital Qi is a function of the old coordinates and conjugate momenta and time t, and the new conjugate momenta capital P i's are functions of the old coordinates and momenta and the time t. We thus have the new coordinates defined in terms of old coordinates and momenta. The Hamilton equation of motion in terms of the old coordinates are Qi dot is equal to dh, the partial derivative of the Hamiltonian with respect to Pi, and Pi dot is equal to minus the partial derivative of the Hamiltonian with respect to Qi. The Hamiltonian h is a function of 2n coordinates and time. So in going from one set of coordinates to another through a transformation which we defined earlier, we would be interested only in transformations which are called canonical transformations. These transformations are such that they maintain the form of Hamiltonian equations in terms of the new Hamiltonian function h prime, which is a function of new coordinates and new conjugate momenta, that is capital Q, capital P and T. Namely, we are interested only in canonical transformations which give us the Hamiltonian equation capital Qi dot is equal to partial derivative of the new Hamiltonian h prime with respect to the new conjugate momenta Pi, and the new conjugate momenta Pi dot is equal to minus partial derivative of h prime with respect to the new coordinate Qi. Thus, if capital Q and capital P have to be canonical coordinates satisfying the Hamilton's equation, they should be derivable from a new Hamiltonian principle, just as the old coordinates Q and P satisfy an extremum principle, namely delta, the change in the expression in the integral t1 to t2 pi qi dot minus h dt is equal to 0. So the new coordinates and momenta should also be derivable, and the equations of motion should be derivable from a similar extremum principle for new Hamiltonian h prime. The simultaneous validity of these two equations mean that the integrand of these two equations can differ by at most a total derivative of an arbitrary function f. Now this arbitrary function f in general can be a function of 2n old and 2n new coordinates, that is q1, q2, q1, p1, p2, pn, capital Q1, q2, capital Q1 and capital P1, p2, pn, and that is the difference can be expressed as a total derivative. The difference of these two equations can be expressed as integral t1 to t2 total derivative of df by dt integrated over dt as the value of this function at the difference of this function at the two extreme values. And therefore the variation delta f2 minus f1 must be equal to 0 because the variations vanish at the endpoints. This function f is called the generating function of the transformation, and once the function f is given, the transformations are fully known. The transformations from the old coordinates to the new coordinates and old conjugate momenta, the new conjugate momenta are completely known. As mentioned before, this generating function f can be a function of 4n old and new coordinates and conjugate momenta. But the old as well as the new momenta and conjugate momenta are related, so f can be a function of either the old coordinates and the new coordinates, or the old coordinate and the new momenta, or the old momenta and the new coordinates, or the old momenta and the new momenta. In addition, f can contain time explicitly. Thus, for the generating function, we have a choice of 4 different functions, as I mentioned earlier, as given in equation 2110. So for the generating function f1, which is a function of the old and the new coordinates and the time t, then we have sigma pi qi dot minus h minus the same quantity expressed in terms of the new coordinates, namely pi qi dot minus h prime, is equal to total derivative of this f1, which is now a function of the old and the new coordinates alone and the time t. The time derivative of the new function can be expressed in terms of the partial derivatives of this function with respect to the old and new coordinates and with respect to time by using the chain rule as shown in equation 2111. Now, when we equate the coefficients of qi dot and capital Qi dot, we then obtain pi is equal to partial derivative of f1 with respect to qi and capital Pi is the partial derivative of f1 with respect to the new coordinate qi, and therefore the difference between h and h prime is equal to minus df by dt. Thus, once f is known, the transformation equations for the old and the new conjugate momenta are known in terms of the old coordinates qi and the new coordinates capital Qi. Namely, the partial derivative of the old conjugate momenta with respect to the new coordinate dpi dqj is d2f1 by dqj etc. And therefore, we have the partial derivative of the old momenta with respect to the new coordinate equal to minus the partial derivative of the new momenta with respect to the old coordinate, and the other generating functions can be obtained by using the Legendre transformations and the equations which are given in 2112. We thus write for f2, which is a function of the old coordinates and the new momenta and time, as a function f1, which is a function of old and new coordinates alone and time, minus sigma over I capital Qi into partial derivative of f1 with respect to the new coordinates qi. So f2 can be written as f1 plus summation of qi pi, that is a product of new coordinates and momenta. So writing the equation 2010 in terms of f2 using this above relation, we then obtain by equating coefficients of qi dot and capital Pi dot, we obtain the old conjugate momenta pi as a partial derivative of this generating function f2 with respect to the old coordinate qi, and the new coordinate qi is the partial derivative of this f2 with respect to the new conjugate momenta, and h prime is h plus df2 by dt. And further, we can write the partial derivative of the old momenta with respect to the new momenta is equal to the partial derivative of the new coordinate with respect to the old coordinate as shown in equation 2118. Now the generating function f3, which is a function of new coordinates and new conjugate moment and time, can also be obtained from f1 by noting that the old conjugate momenta can be expressed in terms of f1 as the partial derivative of f1 with the old coordinate qi. So we write f3, which is a function of new coordinates and new momenta, as a function f1, which is a function of old coordinates and new coordinates, minus sigma over I qi, the partial derivative of f1 with respect to qi. Following the similar steps, then we can obtain the equation 2121, which relates the partial derivative of the new momenta with respect to the old momenta with the partial derivative of the old coordinates with the new coordinates, and likewise the equation 2124. So we can now collect all these relations between conjugate variables in the equation 2125, and these are all the relations which we have, which is the partial derivative of the new coordinate with respect to the old momenta is equal to minus the partial derivative of the old coordinates, new momenta, so on and so forth. We will now demonstrate the invariance of Poisson bracket under canonical transformations. So under canonical transformations, the Hamiltonian equations keep their form, and we will now demonstrate that under canonical transformations, Poisson bracket remains invariant. So we will first prove the invariance of fundamental brackets for the transform coordinates nu qi and nu pj. That is the fundamental bracket, Poisson bracket, between the new coordinates qi qj is equal to the Poisson bracket between the new momenta pi pj is equal to 0, and the Poisson bracket between the new coordinates and their conjugate momenta is equal to delta ij. Now, from the definition of the Poisson bracket qi qj, we can write qi qj Poisson bracket equal to sigma over k partial derivative of qi with respect to qk and so on as given in equation 21.27. And from the relations which we obtained earlier, we have the partial derivative of the new coordinate with respect to the old momenta is equal to minus the partial derivative of the old coordinates with respect to the new momenta, and likewise for the partial derivatives of the new coordinates and old momenta. So when we substitute this in the expression for qi Poisson bracket between qi and qj, the Poisson bracket turns out to be 0, and in the similar way the Poisson bracket between pi and pj is also equal to 0. Now, since the corresponding to the new coordinate q, capital P is a conjugate variable, their Poisson bracket with respect to the new momenta and coordinates also satisfy, that is the Poisson bracket of qi qj with respect to the new coordinates is equal to the Poisson bracket of pi pj is equal to 0, and we have thus proved that the fundamental Poisson bracket holds. To continue with our illustration of the fact that the fundamental brackets remains invariant, we finally evaluate the bracket between the new coordinates and their conjugate momenta with respect to the old coordinates and the conjugate momenta, and from the definition of this, we have the Poisson bracket between qi pj given by the sum over k, partial derivative of qi with qk into partial derivative of qk with qj, and so on, which is delta ij, and we thus have proved that the fundamental brackets under canonical transformations are invariant. So we have now proved that the fundamental brackets under canonical transformations are invariant. So what remains to be proved is that the general Poisson bracket between two dynamical variables given by some function f of g is also invariant under canonical transformation. What does it mean? It means that we need to prove that the Poisson bracket between two dynamical variables f and g with respect to the old coordinates and momenta is equal to the Poisson bracket between these two dynamical variables with respect to the new coordinates and new momenta. This is straightforward, because if you look at the definition of Poisson bracket fg with respect to the new coordinates and momenta, this is simply equal to sigma over I partial derivative of f with respect to the new coordinate into the partial derivative of g with respect to the new momenta minus the partial derivative of f with respect to the new momenta into the partial derivative of g with respect to old momenta, and using the chain rules of f and g, this can be expressed as shown in the equation. So using the relations we have obtained earlier, it is now straightforward, though a little lengthy, to show that the Poisson bracket between two dynamical variables f and g with respect to the new coordinates and conjugate momenta capital Q and capital P becomes equal to the Poisson bracket between these two dynamical variables with respect to the old coordinates and momenta. So using the relations we have obtained earlier, it is now straightforward, though a little lengthy, to show that the Poisson bracket between two dynamical variables f and g with respect to the new coordinates and conjugate momenta capital Q and capital P becomes equal to the Poisson bracket between these two dynamical variables with respect to the old coordinates and momenta. We have thus shown the invariance of Poisson bracket under canonical transformations. We will now show that for the transformation to the new momenta pi, which is a function of the old coordinates and momenta, and the new coordinate qi, which is a function of old coordinates and momenta, the expression times sigma, that the product of the old momenta pi with the old dqi minus the sum of the product of the new momenta pi with the differential of the new coordinate qi is an exact differential. So we are going to show that if sigma over I of the product of the old momentas pi with the differential of the old coordinates, that is dqi, minus the sum of the product of the new pi with dqi's is an exact differential, then the transformation is canonical. Let us consider the generating function f1, which is a function of the old and the new coordinates. Then the differential of f1 by the chain rule is the sum or the partial derivative of f1 with respect to the old coordinates qi into dqi plus another sum of the partial derivative of f1 with respect to the new coordinates into dqi. Now, using the fact that df1 by dqi is pi and df1 by dqi is minus capital Pi, we obtain the total differential of this generating function f1 is equal to sigma over I of old momenta into dqi minus the new momenta into new dqi. And therefore, if the right-hand side is a perfect differential, the transformation generated by the function f is canonical, because we have already proved if this df is a perfect differential, then the transformations are canonical. Now, with the help of certain examples, we will show whether a particular transformation is canonical or not. So the example we want to consider is a transformation where the new momenta is defined as 1 by q. The new momenta is inverse of the old coordinate, and the new coordinate q is the product of the old momentum into the old coordinate square. To show that this transformation is canonical, if we are able to show that capital P into D capital Q minus small p into D small q is a perfect differential, then this transformation would be canonical. So just differentials D capital Q and D small q, so substitute them and we find that this expression is equal to q dp plus p dq, which is the total derivative of p into q, so which is a perfect differential. Likewise, for the transformation which is given that the new momentum is half times the old momentum square plus the old coordinate square, and the new coordinate is tangent inverse of the quotient of the old coordinates and old momenta. To show that these transformations are canonical, so all we have to do is to compute the differential of the new coordinate capital Q and the differential of the old coordinate small q, and then show that the product of the new momenta with the differential d of the new coordinate minus the old momenta into the differential of the old coordinates is equal to a perfect differential, which we have shown in your slide, and this quantity becomes half the differential of the product PQ, which is a perfect differential. Likewise, for a transformation where capital P, that is the new momenta, are given in terms of the old momenta and coordinates by this relation, the capital P is 2q half 1 plus q half cosine P sine P, and the new coordinate Q is a log of 1 plus q half cosine P. So this can also be proved the same way by taking the differential of the new coordinate and the computing the product of P with new coordinate dq and following the same steps as we did earlier, we can show that it is a perfect differential. As another example, we have to show by using the invariance of Poisson bracket, we have to show that the transformation small q is equal to under root 2p sine q and small p, that is old momenta in terms of the new coordinate, are canonical. So what we need to show that the Poisson bracket between the fundamental Poisson bracket between the new coordinates and momenta are satisfied, which is straightforward to do it, because you can see from here that we have the partial derivative of the new coordinate with respect to the old coordinates equal to p divided by p square by q square, and the partial derivative of capital Q with respect to small p is minus q by p square by q square, and putting it in the definition of the Poisson bracket, we can see that from the definition of the Poisson bracket between the new momenta and coordinates, substituting these things, we can see that the Poisson bracket between the new coordinates q with q is 0 and with new momenta p with p is 0, whereas the Poisson bracket between the new coordinates and momenta is equal to 1. So let us summarize what we have learned in this module. In this module dealing with the canonical transformations, we have learned that a dynamical system with n degrees of freedom is completely specified by the Hamiltonian, which is a function of n generalized coordinates and n corresponding momenta. A transformation from one set of variables to another set of variables is called canonical if the Hamilton's equation of motion retain the same form in the new variables as in the original coordinates, and the Poisson bracket remains invariant under a simultaneous canonical transformation of the coordinates and conjugate momenta. Just as the Hamilton's equations retain their form in variables or in their counterpart of canonically transformed variables, likewise the Poisson bracket remains invariant under canonical transformations.